Okay, it's on canvas, so it's due in a week. Two problems, okay? All right, so the first one is about the behavior of a non-Newtonian fluid. Okay, so it's a polymer solution, and you put it into the viscometer, you can measure the shear stress at different shear rates. Okay, so here's the data. Okay, at various temperatures. Okay, shear rate and stress. So here you're going to calculate viscosity and plot them. Okay, and then determine whether the data here can be described by a power law model. Okay. Now to do this, of course, you may need something like MATLAB or Mathematica, something like that. Okay. Basically, you need to do a curve fit to the experimental data here. Okay. Hopefully, you know how to do that. If not, let me know. I'll show you how. Okay. Even in Excel, you may be able to do it, but I'm not 100% sure there because I don't use that for curve fitting. And then try to explain what you see in this table. Okay, so that's that. And then the second problem, it's about how to use the equation we just derived to solve problems. Okay, so before you've learned how to use the shell balance method to solve a problem like this. So this time you're going to use the equation of continuity and Navier-Stokes to solve this problem. Okay, so, and today we'll discuss another example of how to use these equations to solve problems. Okay. All right. So this is on Canvas. It's due next Thursday. All right, so that's that. Oh, also, I hope you've seen my email I sent you yesterday. So solution number 1 is there. I'm going to upload solution number 2 today, and also the lecture notes for the previous 9 lectures. Okay, so again, I want to remind you, those lecture notes are not, if you just look at those, probably it's going to be very hard to understand. Okay, so I would still encourage you to write your own notes and use that as reference. Okay, so okay, all right. So last time we derived the Navier-Stokes, and then this is our attempt of trying to use those equations. Okay, or learning how to solve problems using those equations. Okay, so you can see how you can use all the assumptions to simplify those equations. Okay, so of course in the end, we ended up with the same equation. Okay, so 0 equals to this, and of course you know what happened afterwards, right? So in the previous attempt of solving this problem, we used the shell balance method, right? So we got the stress equation first, okay, and then eventually we got here, okay? So once you got here, of course, the rest of it is the same, okay? Remember, because this is function z, that's function r, so both are constants. You solve for pressure, and then you solve for velocity, and then the stress, and the force, and volumetric flow rate, and everything. Okay, so the rest of it is the same, which means we're not going to repeat those. Okay, all right. So today we're going to discuss another example and see how we can use the Navier-Stokes equation to solve problems. So basically now, with appropriate tools, okay, you can solve the flow of any non-Newtonian fluid with a constant density. How do you do it? Well, you basically use the equation of continuity and the Navier-Stokes. 4 equations, 4 unknowns, okay? So if you cannot find any analytical solution, you can use numerical methods, okay? So this is where those commercially available software packages come in, okay? So Fluent, FIDAP, and COMSOL. So there are quite a few of them, okay? So they use numerical methods to solve these problems, but the equations they use, okay, for Newtonian fluids are basically these 4 equations, okay? So here, of course, we can only look at some simple examples, okay, where we can get analytical solutions. So here's another one. Hopefully this will help you to work on the second problem of the homework. So here, it's basically another device we can use to measure the viscosities of fluids. Okay, it's called a Kuta viscometer. Okay, so this is of course different from the capillary and cone plate viscometers. Okay, so the three most popular viscometers are these 3: capillary viscometer, this is tube, and then the cone plate, and then this one. Okay, so. And today we'll look at how it works and say, if you want to design something like this, what are the equations that are most sort of relevant in this case? Okay. So basically, this viscometer has a cylinder like this, suspended by a wire or something, okay? And then, of course, outside, you have a cylindrical container like this, okay? And then at the bottom, the container is connected to a motor. That can rotate the outside cylindrical container. Okay, so that's basically that. Okay. So of course, when you do the measurements, you put fluids in between the inner cylinder and the outside cylindrical container. Okay. So of course, you use the motor to rotate the container of the outside cylinder. Okay. And then by monitoring the rotation of the inner cylinder, okay, you can measure the torque or moment that's applied by the moving fluid to the inner cylinder. Okay, by measuring the torque, of course, all the geometrical parameters like the radius of the inner cylinder and the outside cylinder, and knowing the speed here, okay, how fast it's rotating, all right, and then you can calculate the viscosity of the fluid, okay. So that's basically how it works, okay. Now you may wonder how the torque or the moment that's acting on the inner cylinder can be measured, okay. So if you have taken 240 before, if you have studied the twist of a cylinder there, okay, I don't know whether you have, because when I taught it, I did discuss that, then it's a piece of cake, to measure the torque that's acting on this wire. Okay, so all you need is put a mirror there, okay, and measure what's the angle of twist, okay. So then you can get the torque. Anyway, so that's that. Okay, but here we'll just assume that that's measured, or that's a known parameter already. Okay, all right. So this is the problem. So of course, before you solve any problem, you see the problem description. The first thing you need to decide is which coordinate system you should use. Okay. So in this case, it's obvious, right? Most of the time, it's obvious. Okay. It's cylinder, so it's the cylindrical coordinate system. Okay. So R direction and Z direction on the top, R and Z, okay? And the angular speed of the outer cylinder here in that direction, omega 0, okay? And then the radii of the two cylinders. So this is the cross section. The radius of the cylindrical container, that's capital R, and the radius of the inner cylinder is lambda R. Okay? All right. So of course, now we need to make some assumptions. We're going to assume it's steady state, okay? Which means at the moment you start to rotate the outside cylinder, so maybe everything is still, in sort of the developing mode, okay? Just like a tube flow. At the entrance, then you may not have a velocity profile that's as stable, or everything is still changing, basically, okay? But once you rotate this for a while, and then you can imagine that the flow inside the container will reach steady state, which means, everything there will not change over time anymore, okay? So this is a common assumption, as long as you keep the flow field there, nothing else changes. As long as you wait long enough, you can reach the steady state, right? Of course, mathematically, that simply means that derivative is 0, okay? And then we're going to assume it's a long cylinder. Of course, I'm sure when people design this viscometer, they consider this problem theoretically first, okay? So long cylinder in momentum transport, it simply means what? When you say this word long, it simply means what? It's infinitely long, like before, okay? So of course, that means when you design this, you want to make sure the length of this compared with the radii there is much larger, okay? So that you can make this assumption, okay? And if it's very long, that simply means what? So if this two cylinders are infinitely long, okay, the outside cylinder is rotating. So that means no matter where you look at this problem, it's going to be the same, right? Since this is infinitely long, you close your eyes, move the cylinder a little bit, you won't notice any difference, right? So now what can we get from there? If anywhere we look at, there's no difference. So that means we know when you rotate this, the fluid will have which component of the velocity. So in which direction the fluid is moving. Theta direction, right? Okay? So that means if anywhere you look at is the same, so that means that velocity will not depend on Z, right? Okay. What else can we get from here? So I mentioned that if this cylinder is like evenly long, no matter where you look at, it's the same, okay? So that's like you also have a plane of symmetry, right? Okay? So this plane here, the R theta plane. No matter where you put that plane, okay? That plane is so the problem should be symmetric about that, okay? Now of course, because of that, VZ should be 0. So the same reasoning, like the one we got V theta equal to 0 in the previous example, the tube flow, okay? So this plane of symmetry will give us VZ equal to 0. Okay? Do we have axis symmetry? Of course, just like before. We also have axis symmetry. And of course, mathematically, that means this derivative is 0. Okay? So once you apply all the assumptions, and we can look at how we can simplify the equation of continuity. Okay, so cylindrical coordinate system. This is the equation. Remember steady state, so we know this is 0. Okay, and we know VZ is 0, so that's gone. And V theta is not 0. However, we have what? Axis symmetry. Partial theta is 0. Okay, so again, we'll end up with this equal to 0. Okay? So this equals 0. It's a derivative in the R direction. Okay? All right? So again, that means what? Rho is constant, so that's gone. RVR is a constant, right? So RVR is a constant. You know, on the wall, R is not 0, but velocity is 0, right? Okay? This one. Okay? That's not 0, sorry. But this one is 0, right? But this one in the R direction is 0 too. But anyway, so no matter which one you use, you know that RVR is 0, right? Just like before. So just like the previous example, if you look at this point, if you look at the equation of continuity, you can get VR equals 0. Okay? So of course, now we know the flow there has only one component, that's V theta. Since partial t is 0, partial z is 0, partial theta is 0, so that means this velocity will not depend on t, z, or r, or theta, which means it's only a function of r. Okay? So this is from these few simple assumptions. Okay? And now we can look at, since now we've used the equation of continuity, now we can look at what kind of equation can we get from the Navier-Stokes. Okay? So, VR is 0, right? 0, 0, 0, and 0. V theta is not 0. Okay? So this term stays. Pressure gradient, VR, VR, VR. V theta is not 0. However, this derivative is partial theta, so this is 0. Okay? Now, gravity, in this case, it's pointing down. Okay. So the direction of the gravity, so that means in the r direction, gr will be 0. So first equation, 2 terms left. This and this, okay? So that's from the Navier-Stokes. So the Navier-Stokes equation. First one, rho v theta squared r is equal to negative p and r. So this equation is where it's different from the cube flow, right? So there we got partial p partial r equals 0, but here no, because v theta is not 0. And the theta component. So go to the second equation, partial t. Okay? VR is 0, so this one's gone. V theta is not 0, but again, partial theta. Okay? Vz is 0. VR is here, so the whole left-hand side is 0. Partial p, partial theta. P theta does change in the r direction, right? So these two remains. Partial theta, partial z, partial theta, and g theta is 0. So, sorry, I said 2 terms remain, right? Actually, see partial theta, okay? So this one's 0 too. Actually, only one remains. So second equation is 0 equals to mu ddr 1 over r d dr r d theta and that. So that's the second. And now the third equation, so Vz is all 0, right? So the whole left-hand side is 0. Negative p, partial z, Vz 0, 0, 0, and gravity, right? So third one is 0 equals to negative partial p, partial z, minus rho and g. So these are the equations we have, okay? So as you can see, we don't have to use shell balance methods anymore, right? Because we're directly using the equations derived from, okay? So you look at these 3 equations, okay? So the first and the third they're about what? Pressure. Question?
Wasn't the partial derivative with c when it equals 0?
Sorry?
The first term on the last equation wouldn't that be 0 since it's the partial derivative with respect to c?
Good question. So, yeah, so this p here, partial p, partial z, should this be 0 or not? Because, yeah, we did sort of wrote something like this, right? Should this pressure be 0 too? So should this gradient be 0? Yeah, so it's not 0 because if it is 0, that means the gravity will have nothing to nowhere to go, right? You have 0 equals to negative rho g. Obviously, that's incorrect. So now what's going on? Why did we say this here? And then later, we know this partial p partial z cannot be 0. This is why you come to classes, right? So.
The pressure always points inward, so it's going to be an opposite direction.
Yeah, so basically here, that partial z that's equal to 0 we've sort of concluded earlier, okay? This applies to what? The flow field, okay? It's about the flow, the velocity, okay? So, which means you wait along, the symmetry, okay? So, in this case, because of gravity, okay, you look at the pressure applied by air to fluid, that's all the same, okay? However, when you look at the pressure produced by gravity, it's not, it is dependent on the z direction, okay? So that's the reason why this one is not 0, okay? So in other words, the static pressure does change in the z direction because of gravity, okay? Imagine if there's no gravity, yeah, so pressure everywhere would be the same, okay? All right, so again, that's because, see, this only applies to the velocity, okay? So we got from the long cylinder, right? So you're looking at a velocity component in v theta direction. So basically, anywhere you look at, you don't expect that v theta to be different, okay? So that's that. All right? Okay, so 3 equations. As you can see, the first one is the last one, they're about pressure, okay? The second is about velocity. So which means if we want to get the velocity first, we can just solve the second equation. Okay, once you know the second, once you know v theta, you can put it here, and then we'll have the 2 equations about pressure, right? And you can try to solve for pressure, okay? But as you know, if this is a Newtonian fluid, once you know the velocity, you can calculate almost everything that we've calculated before, right? So once you know, well, yeah, let's get the velocity first, okay? So, all right. So to solve that equation, we need boundary conditions. How many boundary conditions do we need? Two, right? Because it's a second order ODE, so we need 2. In this case, of course, the boundaries are kind of easy to identify. And one is on the inner cylinder. What's the velocity on the inner surface of the cylinder? V theta. 0, right? Because the inner cylinder is not moving. So V theta is 0 there. And the other boundary is on the inside of the outer cylinder. What's the velocity there? V theta. So we know the angular speed, right? So omega 0 times r, right? Okay? All right. And also, you can see why I drew the angular speed in this direction. And that's what? That's the theta direction, right? Okay? So this way, you know, you can write v theta as omega 0 r. Okay? Otherwise, what if I drew the angular speed in the other direction? Then v theta should be negative. Okay? All right? So make sure you know all the directions and get them right. All right, so 2 boundary conditions. Of course, we can just solve this equation. And the way to solve this, that's easy, right? So 0 mu is gone, EDR. So you integrate once, you get this equal to constant, right? This equal to constant. Of course, you multiply both sides by r. And then you integrate again. So constant r will give you a constant r squared. divided by 2. That's this equal to that. This equal to that plus another constant, right? So when you divide both sides by r, you get v theta. Okay? And then so v theta should be something like this. Okay? Remember, this equal to, when you integrate this, that's equal to C1R, okay? So you get C1R squared over 2 plus C2, right? So you then divide both sides by R, and that's the solution, okay? So of course, then you determine C1 and C2 using these two conditions, okay? All right? But there's a problem. Oh, that's okay. So no, it's but yeah, so it's okay. So just plug it in, okay? R equals that. This is 0, and that. So you can solve for C1 and C2. So in the end, v theta is equal to lambda r 1 minus lambda squared r divided by lambda r minus lambda r divided by r. Okay? All right. So once you have your solution, of course, it's always good to check whether you get the special values on the boundaries. Okay? Also, you can see when r is equal to the inner radius is 0, it's equal to when it's equal to the outer radius, and you can get this is r 1 over lambda minus lambda minus lambda. So that's exactly this. Okay. So of course that's means 0 r. So everything checks, right? Okay. Checks are good. All right. Once you have the velocity, just like the previous case, okay, tube flow, you can calculate everything you want, okay? So once you have the velocity, for example, if we want to calculate the stress, what do? Where would you go to find the equations we can use to solve for the stress? Handout number either 2 or 3, right? I think it's 3. No. 4. Well, 2. shows you how bad my memory is. All right. Cylindrical. Okay, so we're using the cylindrical particle system. See from here, once you know the velocity, you can come here and calculate any stress component you want. Okay. So in this case, of course, you got the first one, VR 0. V theta, not 0, but partial theta, that's 0. VR, so this one is 0 too. Here, partial VZ, well, VZ is 0. So all the normal stress components are 0. Okay? R theta, V theta, and partial R. Well, this is not 0, but this is 0. Okay? So this is non-0. You got this one, partial theta, and partial Z. Partial V theta, partial Z, so that's 0. Here, RZ, ZR, VR, VZ, 0. So the only one that's not 0 is this one, tau R theta, or tau theta R, okay? So then we plug the velocity into this equation to get tau R theta. Oh, before we do that, actually, I also wrote this solution in a different format. I guess this way it's easier to see. So handout number 2. negative. Mu r partial r and d theta of r. So that equation here. Mu r dr d theta divided by r. So the reason why I wrote this equation with a different format with an r here is because, as you can see, here we have v theta of r, right? So it's much easier. Then you know this r will cancel, and then we just need to do the derivative of that to get the stress, right? Okay? So this is equal to negative 2 mu equals 0 lambda squared 1 minus lambda squared r over r squared. So this is the stress. Not just the stress on the walls, it's the stress anywhere in the fluid. Okay? All right. So we know lambda is less than 1, right? Okay, the inner radius, of course, is smaller than the outer radius, so lambda is less than 1. So this is larger than 0, okay? Larger than 0, larger than 0, larger than 0. This shows what? Tau r theta is negative, right? Okay, tau r theta is less than 0. Okay, so that can help us to figure out the direction of the stress on the cylinder, right? Because eventually we need to calculate what? We need to calculate the torque that's acting on the cylinder. To calculate torque, as you know, you need to know the force. To know the force, you need to know the stress. Stress multiplied by area will give you the force, right? So now we know the stress, tau r theta. So tau r theta on the inner radius, inner cylinder surface. So let's calculate the magnitude first. So on the inner cylinder surface, that's what the radius is equal to. So for us, tau r theta there is equal to, you just need to plug in this r over there, okay? And you know this is negative 2 mu omega 0 over 1 minus lambda squared. Again, this is less than 0. So this will help us figure out the direction of stress on the inner cylinder, right? So if we look at the cylinder from the top, okay? Meaning that if we look from there down and look at the surface, look at this cross section, all right. So that's the surface we're looking at. That's the r direction. Remember, we're looking at the cylinder from the top, okay? So theta direction would be that direction, okay? So, the stress, what's the direction of the stress? So tau r theta, I shouldn't write tau r theta. I should just write the magnitude. So we know this is the magnitude of the stress tau r theta. What's the direction? Up? Well, on this side. That way or this way. Up or down? Up, right? Or down? Yeah, so up, right? Okay. That's because, see, positive, negative, negative, positive. You look at the normal direction of the surface is in the r direction, right? So if the stress is positive, it should point to the negative theta direction. But in this case, the stress is negative. So that's the direction of the stress, okay? Which makes sense, right? Because, see, it's rotating that way. Of course, the fluid is flowing that way here. It's going to apply a force in that direction on the inner cylinder. Okay, so theta direction. All right. So we figured out the magnitude and the direction, of course, to calculate the torque. The torque acting on the inner cylinder is simply what? The force times the moment arm, right? Okay. So, what's the moment arm? R, right? Lambda R, okay? And the force is, since the stress is a constant on the surface, is simply, the force is simply the stress times the area of this inner cylinder, right? So the area is simply the circumference of the circle times the length, right? So there we go. So Tz, the torque, you know the direction. Stress times the area, that's the area, will give us this force. Force times the moment arm, lambda r, that's the torque, okay? So 4 pi mu omega 0 r squared L lambda squared 1 minus lambda squared. So that's the torque, as you can see. So the torque can be measured or calculated by knowing the angle of twist of that wire on the top, okay? You know the angle of twist, you know the material, and then you can calculate torques that's acting on the wire, okay? This is measured, of course, mu is what we're trying to calculate. You know the omega 0, you can measure R, you can measure L, lambda, so that's how you calculate mu in this case, okay? So that's how the cutoff viscometer works, okay? All right? Let me calculate one more thing. Although in this case, this parameter or variable, it doesn't really matter that much. If I ask you to calculate the volumetric flow rate that's going through a cross section, how would you do it? So as you know, in this case, we only have what? One velocity component. When you calculate the volumetric flow rate, which is the cross section we should consider? Is it this one? No, because see, there, the velocity is in the theta direction, not perpendicular to this surface, right? When you consider the volumetric flow rate, it's always the cross section of the surface area that's perpendicular to the velocity direction, right? So in this case, when you look here, velocity here is going that way, the velocity here is coming this way, right? So what is the cross section? Well, here we go. That's your cross section, okay? All right? So that's the A, okay? So that's the A. So Q is equal to, in this case, V theta dA, right? So A is that cross section. Now, of course, in this cylindrical coordinate system, we need to figure out how to express, how to write that dA in this coordinate system, okay? So here, the two dimensions that are important are the R direction and Z direction, right? Okay, well that's easy, because R and Z direction, they are just like the rectangular coordinate system, right? So integration 0 to L, z direction, lambda r to r, that's the r direction. dA in the r and z direction is simply dr dz, right? So here we go, v theta dr and dz, right? Okay, yes?
I have a question. The inner cylinder didn't go down to the very bottom of the outer cylinder. So there is like a rectangular surface there.
That's a good question. See, she's very sort of careful. So basically, you look at this problem, the bottom here, well, yeah, so if it cannot sort of touch the bottom surface of the outer cylinder, that's because if it touches there, you're going to have friction, right? So when you move this, there will be friction. That's going to apply torque to this part of the cylinder too, right? So, which is why we assume this is very, very long, okay? We do not let it touch so that we can avoid that friction there. Now, this gap will not be too large. As long as the cylinder is long enough, of course, you can imagine the fluid here will move a little bit too. Will also rotate, right? So that's going to apply some torque to this surface area too. However, if this is very long, that means the torque applied by on these surface will be much larger than the torque applied here. So that part can be neglected. Okay? All right, so. So we know the velocity, right? So the next thing you do is put that velocity here and do the integration, okay? So velocity is here. Let's see which one to use. This one's better for that purpose because when you do the integration, two functions here. If you use this one, it's kind of complicated, right? So if, look at this one, you do integration in the r direction, you get r squared, you get a log term, right? So z does not depend on z. So z direction is easy, just L. So this is what we're going to get. So equals to just L lambda r and r so when u is 0, lambda r 1 minus lambda squared, which is constant, r is the same. Yep. Lambda r and lambda r and r and dr. All right. So put all the constants together. R 1 minus lambda squared. So r squared divided by 2. And then r squared minus lambda squared lambda r squared. So we can factor the r squared out. So divide by 2 lambda r. So that's the first one. Okay. And then log there. So minus lambda r log r. So log r minus log lambda r, as you know, that is basically log r over lambda r, so log 1 over lambda. Okay? Of course, to further simplify this, how do we do it? Negative plus, so L 0. where? Yes. Okay, so that's the volumetric fluid. Of course, once you have this, you can calculate the average velocity easily, right? Okay, all right. And this is equal to average velocity times the cross-sectional area, which is LR, which is basically the area of this rectangle, right? So L and this length is R minus lambda R. So that's the area. Average velocity, right? Okay. All right. So what else can we calculate? Well, as mentioned earlier, there are two more equations we didn't use here, right? So I said, once you know B theta, you can put that here and calculate pressure coupled with this equation, okay? So that's a little beyond what we want to do here because two partial differential equations, right? As you can see, P depends on Z and R, okay? All right, so we won't do that because the math is a little more than I want you to do, okay? Partial differential, PDEs. But you can do it, right? So it's not that complicated, but still. We won't do PDEs here, okay? All right, so there you can get the pressure, which is a function of R and Z, okay? Okay? Yes?
If the cylinder is horizontal, then will the pressure be dependent on Z?
That's a good question. That's going to make things a little more complicated because that's a good question too. So you turn the cylinder 90 degrees, okay? Now the cylinder is horizontal and the gravity is pointing down. You look at this problem, it becomes much more complicated, right? So first of all, do we still have axis symmetry? Not anymore, right? Because now the gravity is in what direction? It's not even in the R direction because, R direction varies, right? So you have a cylinder here, right? Gravity is in that direction, but R direction is, sort of pointing anyway, right? So the gravity is not even in any coordinate direction. So the gravity is going to cause this problem to become a non-axis symmetric problem, okay? So that means all these partial thetas you cannot get rid of, all right? So you still have a long cylinder, which is good, okay? But the problem will depend on R and theta. So that becomes so basically there'll be two equations you have to solve together. Not like now, we can just solve one and we get the velocity and then we can solve for pressure too. But there, the two equations will be coupled together, or the two coordinates, right? So it's here. So the problem will depend on R and theta, okay? So it's a much complex problem. So this, maybe I should say something about the design, okay? So this, when you design things, you want to try to make things simple, okay? So although design is not our main sort of point of discussion here, but I'm sure you heard about this simple engineering design principle, the KISS principle, right? Since today is Valentine's Day. So KISS represents not Valentine's kiss, but represents keep it simple and stupid. Okay, so when you design this, obviously, if you realize that, you know if the cylinder is oriented sort of in a vertical way compared with the horizontal way, the vertical way is a much easier problem to analyze to get the equation that allows you to calculate the viscosity. And then, of course, when you design this, you want to design it this way, okay? And also from here, you know that if the cylinder is not very long, okay, so then the problem will also depend on the z direction. And then, of course, you know, again, it's a complex problem, and you don't want to do that. You want to keep it as simple as possible, okay? As long as it does the trick, the simpler, the better, right? Okay? Other questions or things you want to discuss? Anyway, so when you try to solve a problem using the equation of continuity and the Navier-Stokes, try to look for the key words, okay? Whether it's steady state, whether the problem has axis symmetry or other symmetry, you know, planes of symmetry, or whether it's symmetric, for example, in spherical, whether it's symmetric about theta or phi, you know, and then you start with these equations and see which terms are zero, okay, and hopefully you'll end up with an equation you can solve analytically, okay. So, yeah, we don't deal with numerical methods here, so that means any problem you're going to see in homework and exam, there are going to be problems where you can get analytical solutions. Okay, all right. Hopefully this is enough for you to practice. All right, so the next problem we're going to look at is the cell sedimentation problem. So this is related to that test that the doctors do in the hospitals about whether your cells are falling to the bottom of the test tube fast or slow. Okay, so this is related to that, or this is why we're looking at this problem. First of all, this kind of problem is, yes?
What is that test? What does the
It's
speed
called,
of the cell
I believe it's called ESR, erythrocyte sedimentation rate.
What does it mean?
So basically, if you have infection and several other diseases, and your cells will tend to fall faster due to gravity. Before, you have to really put the blood into a capillary tube and put that tube there and look at, after some time, and look at, the length of the red blood cells, basically. But nowadays, I believe everything's automatic. You put it into a machine, it's going to tell you the values. Yeah. So there, it's mainly red blood cells, of course. But, well, yeah. But to start, we're going to look at a sphere. As you know, a red blood cell is not really a sphere, but we'll start with a sphere, and then I'll let you know how to deal with the shape of the red blood cells later. Okay. But first of all, this is a Stokes flow. So you may still remember what is a Stokes flow, right? So Stokes flow, another term for it is, which is easier to understand and remember, the low Reynolds number flow. Okay. Now the reason, of course, that because now we're dealing with a single cell moving in a large fluid. Okay. So of course, because the length scale is so small on the order of microns, when you calculate the Reynolds number rho UL, right? L is very small. Velocity is not that large, okay? Because the beginning is 0, it gradually accelerates. It's going to reach a velocity that's not too large, okay? So as a result, Reynolds number is always small. So this is a Stokes flow, and we're going to start with a sphere. Why? Because sphere is simpler, okay? All right. So basically we're going to look at a sphere moving in a Newtonian fluid. So the reason, of course, because plasma is Newtonian, okay? So no problem there. The radius of the sphere is r. Okay? All right, so this is the problem. You have a sphere, and it's moving in a large volume of fluid. Large volume. Now you may wonder that, well, there are so many red blood cells. How can you just look at one and assume it's a large volume? Well, there are other effects when you have multiple cells or more cells, which I'll mention later, okay? But for now, it's just one cell moving in a large volume of fluid, okay? So a simple problem. Now, of course, one way to do this is to change your vantage point. So before, it's like we're sitting in the fluid and look at the cell moving, right? So now we'll change our position. Instead of sitting in the fluid, now we go sit on the cell. When you sit on the cell, what would you see? You don't see the cell moving, right? You're moving with the cell. You see, what you see is the moving of the fluid, right? Okay, it's like a coordinate transformation. Okay, so instead of looking at a sphere moving through a fluid, now we're looking at, well, the fluid is moving along a sphere. Okay, so and the velocity here is v infinity. Why? Because if the sphere is not moving, so that means when the fluid flows around the sphere, the velocity here will be, sort of at many different values, right? But if you look at the far field velocity there, we can assume it's constant. Okay? So in other words, so before the sphere is moving at a constant velocity. Okay? And now we sit, and that velocity is this. And now we sit on the sphere and look at the fluid moving around it. Of course, when that happens, only the far field, very far away from the cell or sphere, the velocity is the velocity of the sphere before. Okay? Okay? So it's like a simple coordinate transformation. So, can we solve this problem? Yes, we can. Okay? However, this is a complex problem. That's because you have to deal with these equations, okay, in the spherical coordinate system, okay? The math is complex, and you can do it, okay? It's just too long, okay? So because of that, we're not going to do it. I'm sure you don't want to see me writing all the equations here, okay? Instead, I'll give you the solution. because our goal is not the complex math here. Our goal is to learn how to use this solution to look at how a cell will move in a large volume of fluid. So that's V sub, and this is V sub theta. Negative 1. So negative 1. Plus R 1/4 All right, look at VR and V theta. They make sort of perfect sense, because when you let R go to infinity, you get the two components of the velocity VR and V theta direction. See, remember here, V infinity is in that direction. It is in the Z direction, okay? So that velocity, okay, will have two components in the R and theta direction, right? So remember, it's the Z direction, right? So you would, in a spherical coordinate system, you don't have Z. You only have R, theta, and phi, okay? So it's going in that direction, so R will be anywhere there. So remember that angle between R and Z is theta. So that's why V infinity cosine theta in the far field will be one of the components of that velocity. And of course, you have another component in the V theta direction. If you have trouble visualizing these two velocity components, I would use that MATLAB figure I put on canvas, right? Showing you the different volumetric elements in the cylindrical and spherical. So try to use that to visualize these two velocity components, okay? Now I didn't write V sub phi. What do you think that is? 0, okay? That's because, see, that's the velocity, right? The phi direction is perpendicular to this direction, the Z direction. So that one's 0. And the pressure is also solved. P0 minus rho GZ minus this mu V R squared cosine theta. So when you look at the pressure here, you know what P0 is, okay? So P0 is the pressure value at Z equal to 0, so right there, okay? And of course, theta is equal to 90 degrees, which means when theta is 0, so that means this angle here is 0. Theta is 90 degrees right here. So that means basically here, okay? On this surface, okay? So in the Z direction, that's basically what? Due to the gravity, okay? All right, this is due to the fluid flow, okay? All right? Okay? All right? So now, once we know the velocity, as you know, we can calculate everything that we want to calculate. One of them that we're always interested in is what? The stress, okay? Handout number 2, on the 3rd page, you see the equations, Newton's law, in the spherical coordinate system, okay? So here, look at the first one, VR partial R. Not 0, right? VR is a function of R and theta, not 0. Now theta, theta. V theta is also a function of R and theta, not 0. This one is 0, because, see, this is 0, okay? All right? And Actually no, sorry. This is not zero either, okay? It's VR and V theta, they're both here. Well, anyway, by looking at this, you know, it may not be zero. So tau r theta, r and theta. So this is zero, this is zero. So this one's zero. And this one, partial phi, zero. And v phi, zero. So this is zero. So these four may not be zero, okay? All right, so we go to handout number 2. You can calculate these stresses. So this is tau RR. So all you need to do is to plug in that V sub r here and do this derivative, and you have this stress. And then of course you plug others in to get this one. And you'll find out that once you have the final results, it's basically negative half of this one. This one is equal to that. And the last one, tau r theta, is equal to mu v r. It's interesting to look at the directions, okay? So when you look at tau r, okay, for example, since we're working with a sphere, eventually we'll be interested in looking at the stress right on the spherical surface, right? So on that surface, if you're trying to figure out whether this is the directions of the stress there, okay? So from here you can see it's going to be more complex than what we've seen before. Why? Because of this term, cosine theta, okay? So what's the range of theta in the spherical coordinate system? 0 to 180 degrees, right? Not 0 to 360. So 0 to pi. From 0 to pi, as you can see, cosine theta will change signs, okay? So that means the tau r here may change from positive to negative. So that means on the spherical surface, this stress, the direction, will change. Will change from the r direction to negative r direction, okay, or the other way around. Anyway, it's going to change. So that's what makes this problem a little more complicated than others. And for the same reason, since this is equal to tau r, there will be a theta in there too. This will change too. This will change too. And of course, this one will change too. However, when you look at theta, theta, remember, is from 0 to pi, right? Sine theta will not change signs, okay? Sine theta will always be positive. So that means this shear stress, the direction will not change, okay? So whatever direction it is, it's always in the same direction, okay? And of course, you know, it's as long as this is larger than 0 in the z direction, you know this is larger than 0, so of course you know in which direction this shear stress points to. Since we've gone over this so many times, I won't repeat them, okay? So of course, we mentioned this before. I just want to write it here. All other stresses are 0. Okay? And what we'll do next is to look at the force exerted on the sphere, especially the force in the z direction. You may look at the other directions too, but in the x and y direction, they're 0. And of course, in the spherical coordinate system, and once you have z, that means this force will have components in the r and theta direction. Again, the theta direction is 0. Okay, so just like the velocities. Okay. Well, yeah. So I'll stop here, and we'll finish this next time.